Okay, so we will continue to finish the MPI chapter. So the last thing we will teach about MPI is the MPI I/O interface. So as we mentioned, right, I/O is actually very important to performance because I/O is the slowest among all the resources, right, such as processing and memory access time. um, the disk access time usually is tens or even hundreds times slower than the memory access time. So especially nowadays, we have lots of data-driven computations, including AI, deep learning. All those computation require to access a large volume of data during the computation. So the data access time become very important, and of course the I/O performance could easily become the performance bottleneck. So how can we achieve better data access time or higher data access bandwidth? As we mentioned, right, when we introduce the architecture or the technology of supercomputers, we mentioned those parallel file systems, right? So for the storage system, it's also get parallelized, and it is built on top of multiple machines. So each of those storage nodes can direct access by the compute node. So if we can have individual or independent network bandwidth between each pair of compute node and storage node, then we are able to further parallelize the I/O bandwidth. Okay? So that's why we have those parallel file system. And the parallel file system is a necessary mean to achieve that. Because as you can see the problem below, um, uh, the parallel file system provides those parallel I/O, and besides, we also need a parallel I/O library to collaborate with the file system, so we can actually utilize those parallel I/O bandwidths. So as shown at the figure below, right? If we only have a single file, if we want to utilize the parallel file system to access a single file, then remember for an MPI job, it actually consists of multiple tasks, right? Like P1 to P4 over here. And if they don't coordinate among themselves, they try to open the file at the same time and try to operate on the file at the same time. Actually, it can only read the file in parallel, but not to write the file in parallel. Okay, because for file system, it has locks, right? You want to avoid data inconsistency, and so for a file, if you can if it's read only, you can open by multiple processes at the same time, as we all know. But if you open the file with the write permission, then the file system has a lock, right, to only allow a single process to open the file at a time. So that means if you want to do a parallel write, you cannot just simply let those processes try to open the file individually at the same time. Okay, so how to resolve that problem? At the beginning, one of the easiest way is that we will need to partition the file into multiple files. So it's not just a single data set, your original data set. You have to store it by multiple files. Then, of course, each process can then open their own files independently, right? So that allow us to do the parallel write as well. Okay. However, this technique, although even today, some people use it, but this technique has some drawback, right? First of all, if your file is huge, right, you might divide it into many small files. And small files usually create extra burden to the file system because you have to manage more files, right? And if you try to list the files under a folder, then it might take you a very long time if you have too many files under that folder. So for file system, actually, we usually want to reduce the number of files. It's the same for the user, right? Because if you have a single data set, but somehow you have to manage the data set through many files, you also need to remember, right, what's the meaning or which part of the data is in which file. So you have to remember or record down those relationships by the users as well. So it's also create a problem for the users. Okay, and the worst thing is you can see the number of files usually have to depend on the number of processes you want to access the files, right? So if you have four processes, then of course you want to partition the data set into 4 files. But if you want to process data with 10 processes, then you have to repartition the data set into 10 files. And repartition files definitely is a very costly operation, right? So it becomes less flexible for the user as well. And sometimes the number of the current file partition may not give you the optimal I/O performance. Okay, so this techniques also is very easy and it can achieve parallel I/O, but it has a lot of limitation and drawbacks. So, means having a parallel file system alone is not enough, right? Some of the file operation, we still need collaboration between those processes for an MPI job or MPI program. So that's why we have the MPI I/O library, right? Or the MPI I/O interface. Okay? So this interface, basically, as you can imagine, provide those basic file operation like open, read, write, flush, synchronize, etc. Okay? And we need it, especially from the previous example. You can see that, for example, to allow those tasks or processes to operate on the same file, when they call the fopen, this fopen operation, it will actually get coordinated by the MPI library. So the MPI library will merge or at least manage those file opens from the MPI task to a single file open operation to the file system. So for the file system, it will think the file only opened by one process. Okay, and the file handler, right, from your file open operation will then be passed and managed by the library to share between those MPI tasks. So they can all through that single file handler to operate the file. And of course, you might wonder, well, does it really solve everything? Because although it allows the file to be open and accessed by multiple tasks, but how about the problem like data consistency, right? What happens if those tasks try to write the data to the same file location? So in fact, those problems are handled by the user program itself. The MPI library does not solve this problem for the user because only the user knows what's the how they want to perform their I/O operation and how to resolve this concurrent write issues. So it's actually managed by the programmer. And as we will see, the MPI file write API, and so this management is actually quite simple. Usually the principle is that the programmer, right, will ensure each process or each MPI task only write to a certain part of the file. They will not try to write the same file content at the same time. Okay, so that's user's responsibility to coordinate, to decide which region each task should write. So there will be no overlapping between the data they try to write on. Okay, so that's responsibility for the user, not MPI library. The MPI library simply allow the MPI processes to interact with the payroll file system. Okay, all right. So especially for those read-write operation, the MPI library provide two types of I/O for both read and write. Okay? One is collective I/O, the other is independent I/O. And we can look at the independent I/O first, because that's exactly what I was mentioned about how you perform a read-write by the MPI tasks. So independent I/O means that the process will perform the read and write operation independently. Okay, so they are allowed to read and write certain part of file on their own. And in general, right, in principle, the partition they read write on should not have overlap. Okay, because if you write to the same place, then you have data consistent issue, right? So it's it's the programmer when they decide the region they're going to write, they will need to coordinate between the processes to avoid concurrent I/O, concurrent data access. Okay, all right. So this will be the independent I/O. Okay, and what's the problem for independent I/O? Well, the problem for independent I/O is that if the I/O request you perform by each process is very small, maybe say just 4-byte integer, then the I/O behavior, right, collaboratively become you have many small I/O and concurrently issue from a huge number of processes. So we all know, small I/O usually result in inefficient I/O performance. So in that case, independent I/O may not achieve the best I/O performance. Okay, so to resolve that, we have the collective I/O. So collective I/O means that we will collect the data, right? Collect the I/O operation from all the MPI tasks, and then perform them on the profile system at once. Very similar to file open or file close, right? For those management command, they are by default they are collective I/O as well. Means that all the process need to participate the code at the same time. Okay, and collective read and collective write means that you have a buffer managed by the MPI library to coordinate the read-write operation from all the MPI tasks. Okay, so for example, if you want to read the data, and say each process only want to read one data element, right? You have a 100, you have a data array with 100 elements, and you have 100 processes, and you want to have one process read one data item at the same time, so you can read the whole file at once. So in that case, instead of having each process perform their read-write operation independently, it will be much more efficient if we collect the read-write boundary, right, and make it become merge into a huge I/O request and read the whole, say the whole files, right, to the MPI library buffer And then we scatter, right, those data to each of the MPI tasks according to the read-write boundary they requested individually. So that is what we call the collective I/O. So you have a buffer to collect to calculate the read-write boundary and create a huge buffer and try to fill up the buffer by a single I/O request to the file system. So you can merge small I/O to large I/O, so you can have better performance and reduce the number of requests to the file system, so you could suffer less queuing delay, right? And however, the drawback of collective I/O is that you can imagine, because you have a buffer, so your I/O operation actually introduce additional memory copy, right? Because the data need to copy from the file system to the buffer and then to the processes. So actually there's some overhead for collective I/O. And of course, there's also overhead to coordinate the processes, to calculate their boundary, etc. So it does has no extra overhead. So the collective I/O usually will only work well if the individual I/O is small. So you can use a large I/O to improve the data transfer performance and overcome the management overhead we just mentioned. Okay. And another limitation for collective I/O is that because it's a collective I/O, so again, that means all the process need to involve to the code. Okay, so the I/O is synchronized. So that means you will suffer, you could suffer higher or more synchronization overhead. For example, if one of the tasks, because the execution speed is different for each of the MPI tasks. So some tasks may code the collective I/O first, some may code it later, but the one coded first has to wait until the last one to code. Okay, so you may suffer from higher synchronization overhead. Okay, which I/O will give you better performance is all depends on the I/O pattern. And in general, if your individual I/O, the size of individual I/O requests is large enough, then you will prefer to use independent I/O. But if your I/O size is very small and you have many processes also need to read the data from the file, then it might be better to use the collective I/O. And if you do the collective I/O because it's collective code, then you must make sure all the process code the read-write code. Okay, no matter you try to access the data or not. Okay, even say you have 100 processes and you only have 90 data element, right? And so only 90 out of 100 process want to read the data. But for collective I/O, that means all of them need to code the I/O code. But if you don't want to read the data, then the I/O size you can give it to 0. So it will read nothing, but still you need to code the code. Okay, otherwise other process will be hidden there. Okay. Okay, so let's look at the API for MPI/O. All those I think you are pretty familiar with, right? File open, file close, file read write, and file sync. And the collective I/O and the independent I/O we mentioned, you can see that if you have a O, right, at the end of read or write code, then this is a collective I/O. And without or, then it means it's an independent I/O. All the argument you will see, they are the same, but their behavior will be different, like we mentioned. So if it is a O, then you need to make sure all the MPI tasks right, involved in this MPI program must code the right or must code this collective IO code. Okay, otherwise they will wait for it, right? Just like MPI broadcast or MPI O reduce, etc. Okay. All right, and for open, close, and sync, actually all those, most of the IO, most of the API, they are collective code as well, because they are right management code. So supposedly they can only work if all the processes involved in this program make the code. Okay, all right. And the argument for read write, I think we don't need to further introduce it, because it's very exactly the same as the proxy file system code, right? You need to give the file handler, you need to specify the buffer and how much data you want to read or write. Okay, and of course you I didn't list here, but you also have the MPI file seek, right, to move your file the IO position, right, for read write. Okay, so you have to move your pointer and then to read or write the data from that position. Okay, just like the regular file system code. Okay, right. So that's all for the MPI, and for homework one, right? You can also play with this MPI IO operation as well. But you might not see too much of a difference, because unfortunately, the file system we provided in our computer system is just a NFS. It's not a parallel file system. Okay, so you may not see the much of a benefit from parallel IO. Okay, but you are free, feel free to try it. And if you observe some performance differences, you are more than welcome to report that and to discuss that in your report. Okay? All right, so that's it for the MPI. And after the lab on last lecture, I think now you can all be able to use our cluster, right? And I believe the TA have briefly introduced the homework one spec. Okay, so here I will not repeat too much, but basically your homework one is to implement the R-even sort algorithm using MPI. Okay, and the algorithm should be pretty easy to understand, right? So it divided into even phase and odd phase, and so the number will only exchange between its neighbor on the left side and the right side. And when you compare and switch your number with your neighbor, you always try to push the number, try to sort it, right, by pushing the say the larger number to the right side and the smaller number to the left side. So eventually your numbers will be sorted. Okay, and you might think this is naive and probably slow parallel algorithm. But as the matter of fact, it's actually not that bad, because the R-even sort can fully utilize the computing power of each processes, right? You can see the loading is very evenly distributed among all the processes. And the operation is very simple, right? So it's very easy to implement without too much or unnecessary communication. So it's a parallel sorting algorithm that can be implemented efficiently. Okay? All right. So also because the communication pattern is simple, so I think this is a very good example for you to start your MPI programming. Okay? And we have the pseudocode, which, as you can imagine, probably is not too hard to understand. And your goal is to implement it in parallel, right? and intuitively the behavior just like we described, right? All you need is to write some branch and to identify whether it's the odd phase or the even phase, and then so each process can know whether he should contact the neighbor on the left side or the right side, right? And then just data swapping and compare and swap operation, right? Then you can keep repeating, and then you can get the result, right? All right. So yeah, so the algorithm is not that complicated, and but it's your first time to write a parallel program, so you might need to twist your thinking, right? To make your brain to think in parallel, to imagine how a single process will do, so you can collaborate with other process to complete the whole computation. Okay. And of course, the goal of this course is to optimize performance, right? So you can attempt any performance optimization technique, okay? As long as it still follow the odd even sort principle, that is the communication is only allowed between your neighbor processes, okay? Except at the beginning, at the end, right? When you have to say maybe scatter the number and gather the result, okay? But in between, in the for loop iterations, every process can only communicate to his neighbor. Okay, as long as you follow this communication pattern, then you are you are allowed to do any optimization techniques. Okay, and just as a hint, actually, one of the performance bottleneck, or one of the more time-consuming operation that you will find is doing the memory allocation. So if you are able to reuse the buffer for sending and receiving message, you will see the performance will actually be much better. Okay, and also for a single process, right? We also didn't restrict you on how to distribute the data, right? So, for example, you might want to evenly distribute the data to those processes. Okay, it's not straightforward because the number of items may not be evenly divided by the number of processes. So you get to decide, right, how you want to distribute those data. Okay, and also a process will certainly handle multiple data or data elements, right? Not just a single data element. So within the process, right, given your subarray, you can do any way to sort the data or any computation. It doesn't violate our requirement. Okay, so you could use some more efficient sorting algorithm inside a process. Okay. All right, so basic that's it, and you can also try any sorting library internally within the process as well. Okay, so if you do that, then I think you will find that performance will be improved quite a bit. Okay, all right, so that's it for our the chapter for MPI. Okay, all right, let me start recording.